welcome. In this lecture, we are going to talk about benefit of constant off time and on time digital current mode control with some aspect of FPGA implementation. So, in this lecture, we will want to discuss current loop stability aspect in constant on off time mixed signal current mode control. Then we will discuss some FPGA implementation aspect of on off time mixed signal current mode control, and finally comparative study of fixed frequency and ripple based current mode control. So, here if we consider mixed signal peak current mode control, we have discussed in multiple lecture including in lecture number 93, and we are not going to spend time here. We are talking about peak current mode fixed frequency control. So, if we consider that peak current mode mixed signal control, we have actually discussed the FPGA implementation. That means, this look like we want to implement a digital controller like a digital IC, and this will be sitting inside the FPGA, and we are implementing using Verilog HDL. That means, we are going to use Verilog HDL, and this we are going to using and synthesize, and then it will be plug into the FPGA device, and it will take the data ADC data, and then it will send the DAC data, and the comparator will come out. So, this part we have discussed I think in week 8 of the detailed implementation of mixed signal current mode control. Now, if we go to constant off time, it is a peak current mode control, and it is the same architecture. That means, if we take the peak current reference, it is the same current mode peak current mode control, but in this case here after touching. So, compared to fixed frequency here, this time is constant. So, off time is constant, and the on time actually come out from the loop. That means, once you turn off the switch, it will go to the monoshot timer. So, it will go to the monoshot timer, and then monoshot timer will, once it finishes counting, then it will turn on, and again the current will rise when it hit the peak current limit, then it will turn off. So, this process will continue, and in this case all implementation is same. That means, your ADC DAC controller, and the current loop is also in analog, but here after the comparator output we have this monoshot timer instead of latch circuit and for fixed frequency, and here we also need to consider the minimum on time. Now, we want to implement this constant off time control using a digital platform, that is FPGA. Again, these blocks are common, which we have discussed for mixed signal peak current mode control fixed frequency. The only difference here, and this current reference block, register, everything controller, everything remains same, but here the difference is the modulator. So, here we are going to consider a constant off time modulator, and we will be discussing in the subsequent lecture details of Verilog implementation. But this is the, as if it looks like this whole digital circuit is implemented inside the FPGA. And we know from the current loop stability of the mixed signal current mode control, if we write the final current, it will be in terms of IRFN and M2F. But if we do not perturb, that means, if we take IRF perturbation, if we take it 0, then if you just take this current perturbation, it will be same of IRF perturbation, and this will be 0. So, that means, the current loop will never become unstable when you apply a fixed current reference, but it may be unstable with closed loop when the IRFN will come into picture when you close the loop. But otherwise, if you apply a fixed current reference, it will never become unstable irrespective of the duty ratio, and that makes the inherent current loop stability and very popular for wide duty ratio operation. Now, if we take constant on time mixed signal current mode control, the only difference will be you are using a monoshot timer for constant on time, and there is a minimum off time also you have to consider, and we have to suitably consider this edge detection circuit, and we will be implementing this constant on time control for both voltage base and current base in the subsequent lecture in Verilog. So, we will hold on for further discussion of this implementation. Now, we can also implement this constant on time control within the FPGA. It will look like a digital IC, where only difference compared to the previous one is the your constant on time modulator, and we will discuss about this modulator functionality in detail as well as Verilog implementation in the subsequent lecture. Now, if we compare what is the benefit, so we saw that pulse width modulation, that means if you take the peak current mode control, then there is a stability aspect for duty ratio less than 0.5, sorry greater than 0.5, you need to add RAM, and this RAM compensation also has a problem for precise current regulation, okay, and it is also well known that it will also have an impact on the transient performance if we add too much RAM. But if we take constant on time or constant off time current mode control, then there is no stability aspect. But here the penalty is if you consider the current ripple under constant on time control for a buck converter, it can be shown that the current ripple is maximum when the input voltage is maximum. For pulse width modulation also, that means any fixed frequency modulation, it is maximum for minimum input voltage. We are talking about a voltage regulator where V0 is fixed, that means it is with closed loop. But if you take constant off time, you see it is independent of the current ripple, is insensitive to input voltage variation, and we have discussed in detail about this lecture number 23 in our earlier course of NPTEL course. If you take the RMS current, it will be the same as ripple current, because we know the RMS current for the buck converter will be, if you take the square, it is the load current square plus delta IL square by 12. So, since the load current will be same under closed loop, so if IL increases, then RMS current will increase. Switching frequency, for fixed frequency, the switching frequency is fixed, but for constant on time, if the switching frequency will be the highest at lowest input voltage, which is shown here. For constant of time, switching frequency will be highest at the the switching frequency again will be highest at highest input voltage condition, because this will be low, and at highest input voltage condition this will be smallest and this will be highest. Yes, here also, here actually the switching frequency, here switching frequency is highest at the lowest input voltage condition. That means, as you decrease the input voltage, switching frequency will increase, and in this condition the switching frequency will increase if you increase the input voltage. So, in both cases you can go for adaptation in timing parameter. By that way you can make the quasi fixed frequency or fixed frequency operation. So, that is one of the drawback, but you can avoid, you can do it adaptively, because you are using a digital platform, and this timing adaptation is not a problem. You can use a all digital PLL, and we will discuss some aspect in the last week of this adaptation in on time, but you can make more or less fixed frequency with, and you can get the benefit of other feature in terms of stability. So, in summary, we have discussed current loop stability aspect in constant on off time control, it is inherently stable. We have discussed FPGA implementation of constant on off time control, and we are going to, we have also compared their ripple parameter under fixed frequency and ripple based control, and in the subsequent lecture we will show experimental case study of fixed frequency versus this ripple based control, their stability and this impact, and that will be demonstrated in the subsequent lecture. That is it for today. Thank you very much.